Hey everybody, welcome back. Today, this short video is going to give you an overview of regressions. Basically a simple reminder in case you don't remember possibly everything you want to know about how a regression, what a regression is, right? And so what we're looking at here is the basics of how we take data and turn it into a linear regression. So we're going to be talking about a simple or a bivariate regression and talking about what it means when we get a regression result, what it means when we run a regression. And so what we're going to do is use a simple made-up data set that I've created that looks at a causal relationship. And that's the first thing you want to remember about a regression is that we are saying that some variable, x, causes y. And that's the first thing we do when we create our hypothesis for our analysis is we say we're going to make some assumption, right? We're going to say, okay, there's something x that has a causal relationship on y. And that is that y is our dependent variable. Y depends on the value of x. To what extent is the coefficient, usually beta. And so we're going to say that this thing x causes y and is independent. So real quick, we have our x, which is our independent variable. It's also known as our causal variable. And then we have our y, which is dependent on x. We can also think about our x's as being explanatory. So x explains y, and then what we want to know, since we've made this assumption that x is going to have an effect on y, we want to know how big of an effect, and that's what beta tells us. We want to estimate the magnitude of the effect x has on y, the marginal effect of x on y. So in my example, we're going to be talking about x being how many hours a student studies, having a causal effect on grades. And this makes sense, right? Grades don't cause you to study, theoretically, but the more you study, we can expect a positive, significant relationship on your grade. So each additional hour of studying should increase your grade by some amount. So an hour of studying here, a change in x, has a beta-sized effect on y. Hopefully that kind of makes sense. The way statistical software does this is by taking a sample data set that you feed into the software and estimating a linear relationship. And we have more complicated versions of this. We can get into a more complex version of this, and we will. But for now, we're going to do this simple linear approach where we have one x and one y. Okay? So the data set I've got for us in this case looks like this. Hopefully you can see that, where we've got 5 observations, an n of 5. One person studies 5 hours and gets an A. The second person studies 2 hours and gets a C. The third person studies 4 hours and gets a B. The fourth person studies 3 hours, gets a C. The fifth person studies 4 hours and gets an A. And so now we have our x variable, which is our hours of study, so we're going to call that x1. We have our y variable, which is dependent on our x, and then we have a number of them. When you build your own data set, you're going to want it to look like this, where you have observations, and for every observation, you want to have a value for each x and y. And so we'll get to that more when we get to more complicated regressions. In this case, we just have one x and one y, so that's a simple or a bivariate regression, where we just are explaining our variation in y with one variable. So we can look at this a couple of different ways. If we were to take that information and not knock over the chart and graph it, we could graph it in XY space. So remember, we've got an X here and a Y here. And in keeping in with what we've said so far, we want to remember that our X is going to be the hours we've studied. And our Y is going to be our grade. And that's because X is causing Y. That's the important thing about regression that sets it apart from, say, a correlation coefficient. A correlation coefficient just says these things are similar, they're close together. A regression equation says X causes Y. And then I can chart my variables, right? I had a person who studied, let's say, 5 hours and got an A. So I'll put that up here, right? Maybe this is, let's just put a loose framework up here where we've got A, a B, C, a D, and an F. And then we've got 0 hours of study. We've got 1, 2, 3, 4, and 5. Right? So here's the first person. We'll call them X1, Y1. They studied 5 hours and got an A. Right? Ooh, there it is. The second person studied 2 hours and got a C. So I can plot that point. So that's person number 2. Person number 3 studied 4 hours and got a B. We're starting to see a relationship form. That's person number 3. And then person number 4 studied 3 hours and also got a C. And person number 5 studied 4 hours and got an A. And so now we can see here we have all 5 of our observations in XY space, right? And I can number them, right? This was 1, 2, 3, 4, 5. It doesn't super duper matter. What matters is that we have our points here, right? And that you can see them over there on the video. And so, like I said, we have our regression now that says that the grades a person earns are going to be equal to, and this is where we use slope-intercept form to help us understand that. So remember, slope-intercept form says there's some intercept that occurs when x is equal to 0, and then there's some slope that changes the effect of x on y. And so slope-intercept form is originally y equals mx plus b, where there's x, there's y, there's a marginal effect, and there's a coefficient. For our purposes, and there's different ways to write this, but what I'm going to do is I'm going to say y equals alpha is the constant, and then beta 1 is the marginal effect of x1. And we're only using one x. When you get into more complicated regressions, which I'll expect you to do in 145, you're going to use multiple x's. Right? We're going to explain grades with more than just hours of studying. There's other things that play a factor, right? Are you tired? Did you take the prereqs? Have you studied all semester, or is it only one day of studying? Those kinds of things. Maybe the grade you got on the midterm has a determining factor on your grade in the class. But for our purposes, we have our independent variable, which is hours studied. Which determines our dependent variable, which is the grade. And then remember that beta is the marginal effect of x on y. So what this means is, if our regression equation is accurate, we can take some number of hours studied, say, okay, assuming a person studies for 4 hours, we can estimate what their outcome grade would be. Does that make sense? That's what we're kind of doing with this regression equation. We're saying, given a value of x, we can estimate y. And if we look at these points, we have these, here, I'm going to put them in green now. I've got my 1, 2, 3, 4, 5 observations. We can see there's a relationship between x and y. It's positive, right? As x goes up, y goes up. And so what a regression equation does, what statistical software does when it estimates a regression equation, is it estimates this equation to draw a line of best fit. And that means that they're trying to draw a line that goes through these points. And it's going to be y hat equals alpha hat plus beta hat x. And so what that means is, when we put a hat on something, or a caret, that little hat is telling us it's an estimate. So what this regression equation, what this linear regression equation tells us is, given a known value of x, any possible value of x, any number of hours studied from 1 to 1.01 to infinity, we can estimate a b and an a, or a beta and an alpha, that gives us an estimated y. We can estimate the effect of a marginal increase in studying. So how much does one additional hour of studying matter? This line is estimating that. And if we look, this line's pretty good. It almost fits these points. And when we think about OLS regressions, ordinary least squares regressions, what we're talking about is a regression equation that's going to minimize the space between our actual observations and a point here. So if we think about that original data set that I showed y'all, right? Here I've got my people. I have 2 people who studied for 4 hours. Person 3 studied 4 hours and person 5 studied 4 hours. They got different outcomes. Generally, the more you study, the better your grade. The less you study, the worse your grade. But it's possible to get a C with 3 or 2 hours of studying. And it's possible that 4 hours of study can give you an A or a B. And that makes sense in the real world because there is variation, right? Everybody studying the exact same amount doesn't get the same grade. We understand that intuitively. For the regression equation, it means that this one formula can't perfectly predict y's. So there's going to be a difference between the predicted y and the actual value of y, the actual grade earned. So for example, for this person here, person number 2 studied 2 hours and got a grade of a C. This person number, this person studied 2 hours and got a C, sorry. This person studied 3 hours and got a C. The equation isn't going to predict that, but that's what really happened in the real world. So there's going to be a space between the actual value, the green circle, and the predicted value, which is that line of best fit, right? A good regression equation, an ordinary least squares or OLS regression equation, is going to minimize this distance between the actual value and the predicted value. Do I have another purple? I don't. Okay. So the predicted value is y hat given x, whereas the actual value is yx. Does that make sense? So we have a person, a real person in the real world who's in our sample, who studied for 3 hours and got a C. But our equation, based on the data we gave our computer, our statistical software, predicts that for 3 hours of studying, they should have gotten maybe a different grade. And the residuals are the space in between. The difference between y and y hat. When we take residuals, we square them so that we can normalize them all to a positive value so they don't cancel each other out. But that's what we want to do with a regression equation. We want to give our software a lot of these observation points so it can draw a good line of best fit to do a good job of estimating the marginal effect of x on y. Does that make sense? And so then we can go into the world and say, hey, studying more increases grades. By increasing the hours you study, you can increase your grade up to an A. It takes about 5 hours of studying to increase your grade to an A, something like that, right? We can make policy prescriptions using our statistical analysis of our sample of hours studied and grades. And that's why we do this kind of thing. So hopefully that gives you a little bit of a refresher about what a regression does, right? When we do run regression analysis, when we run a regression, when we put our sample data into statistical software, we're inserting observations to help the software draw a line of best fit that helps define the marginal effect of x on y. The more observations we have, the better, the more accurate that regression line is going to be, the more statistically significant it's going to be, and the better it's going to do at measuring the marginal effect of x on y. Hopefully that makes sense. If not, let me know what questions you have, what videos you'd like to see, and what you'd like help with. I'll see you next time.